Assalamualaikum and a very good day to KoSiST organizers and guests. First of all, I would like to thank all of you for attending today's KoSiST conference session, and I also would like to express my gratitude to the KoSiST organizer for giving me opportunity to be an invited speaker today. My name is Azira, and currently I'm a senior lecturer at Faculty of Science and Technology USIM. My research interests are in medical image processing and also biomedical engineering. For today, I would like to present one of my current research titled Echocardiography and Computed Tomographic Image Fusion for the application of cardiovascular imaging. In today's presentation, I will start by introducing the background of my study, which later will be leading to the aim and objective of the current study. I will also go briefly some relevant past year research and highlight the novelty of my study. In the methodology section, I will explain the data collection and the image processing method which I have published in my publication, and also will show you the result and highlight some main findings from the method. And I will conclude the presentation with the overall conclusion from the study and list of the journal and conference paper that I have published within the study period. If you have any question or comment, I'm happy to receive it at the end of my presentation. Human heart is an important organ in the human body, and it functions to pump blood throughout the body via the circulatory system. One of the important structures in the heart is the heart valve. It functions to allow one-directional flow within the heart, which will later prevent the backflow of the blood within the heart. However, the performance of a heart can be hampered from the heart valve disease. Based on statistics, the heart valve disease is an epidemic, not only in the Western country but also in the Asian countries. There is four heart valves: aortic, mitral, tricuspid, and pulmonary valve. A patient can succumb one heart valve disease or multiple heart valve disease at a time. Based on based on health report, aortic and mitral valve disease are the most commonly affect the heart patient to date. Major cause of this from the stenosis and regurgitation defect. Standard treatment of the heart disease involve balloon valvuloplasty or open heart surgery. However, this treatment is invasive, involving surgeon to cut open the patient's chest and heart to repair the valve. This treatment also high risk to patients with severe stenosis and may lead to the morbidity such as renal injury and stroke. As an alternative, TVR and TVI or transcatheter valve replacement or implantation can prescribe to them. This treatment involves physician to make and small incision in patient chest, and a prosthetic valve is inserted through a catheter and implanted within the affected valve. This treatment usually requires intraoperative imaging modality to guide physician during procedure. Currently, the best choice for intraoperative imaging is echocardiography or the ultrasound of the heart. The echocardiography is also primary preoperative imaging modality for the heart valve. It can provide structural information, and due to no radiation, it can be used to provide real-time functional information too. Compared to other intraoperative imaging like fluoroscopy, echocardiography is much cheaper and does not require special room or facility. However, despite these advantages, the echocardiography suffers with poor image quality. The image often affected by speckle noise and limited field of view. There is also issue in maintaining both surgical tool and anatomy in the same time. Due to 2D echocardiography provides only planar images. It can limit the physician with information needed during the procedure. Cardiac CT, by contrast, is applied for pre-procedural assessment of valvular dysfunction to select candidate patient for TVR and TVI. The modality provides essential information critical in treatment planning. It allows quantitative assessment of the valve morphology and severity of the valve dysfunction. CT has been reported to be useful for identifying complications in patients who have undergone aortic or mitral valve surgery. However, due to the use of high dose of ionization radiation, cardiac CT is infeasible to be utilized during treatment procedure as surgical guidance modality. Cardiac CT is also limited in providing functional information on hemodynamics such as transvalvular pressure, gradients, and the presence of regurgitation, which is essential for the surgical guidance. Thus, if we combine or fuse these both modalities, we can establish a multi-modality imaging, where the information from the fusion has good potential to increase the diagnostic accuracy of aortic and mitral valve pathology, as well as facilitating the pre-procedural planning and intra-procedural guidance for surgical procedure of TVR and TVI. The principal step in this fusion process is to bring the different modalities images into spatial alignment, a procedure which we call image registration. So the aim of my study is to develop an automatic 2D to 3D registration framework for the fusion of echocardiography and CT data, specifically targeting to guide aortic and mitral valve surgery. The technique should simultaneously address the issue of temporal synchrony and spatial alignment of moving images, heart images, from intraoperative thoracic echocardiography and preoperative CT data, offering opportunity for novel ways to display composite structural and functional information from both modalities. To achieve this aim, I have three specific objectives. First, to develop image registration and fusion technique for the alignment of echocardiography and CT data to aid diagnosis and guide intra-procedural treatment of aortic and mitral valve disease. Second, to develop an automatic 2D to 3D registration and fusion framework for three different cardiac views, which is in this case, I choose three: Mercedes-Benz sign, long peristernal axis, and four-chamber view without optical tracking information. And the third one is to validate the accuracy of the registration framework for the guidance and of aortic and mitral valve surgery using real clinical data in a retrospective study. So if we go back to see the past research study, image registration is an area of ongoing research. For cardiovascular imaging, there were research done involve intramodality, which is registration between same modality images, and also multimodality, registration of different imaging modality. To date, all the research done only focuses on issue of motion artifact and quantitation of cardiac wall and fluid dynamic. The issue of image guidance for interventional procedure of cardiac valve, which was not critical for their application, was not addressed. An observation of the trend of current literature suggests that very limited studies were introduced to specially align 2D echocardiography and cardiac CT volumetric data. Previous studies are similar in the aspect that optical tracker device is mandatory to track the ultrasound probe position and orientation during echocardiography and CT registration. These techniques are currently limited by cost resolution and the availability of the optical tracker device for clinical application, but merely tested on the phantom and animal studies. In addition, these techniques just adding more complicated tracking equipment to the already busy surgical scene. Image fusion between 3D echography and CT also been studied before, but this specialized ultrasound technology is quite new, require additional user training, and therefore has yet to be widely adopted. In addition, there is additional procedure cost associated with 3D echocardiography imaging, and the limited access to 3D streaming make it is poorly suited for real-time fusion with other modalities. Moreover, little studies have been conducted to study the use of image fusion to assess aortic and mitral valve disease for surgical navigation during TVR and TVI. So to highlight the novelty of my study, the multi-modality fusion technique will address the treatment of TVR, TVI for aortic and mitral valve. Second, rather than adding complicated tracking system to already busy surgical scene, the technique proposed by this study designed a method in which the imaging system is the tracker and the patient is the marker, and we validate the performance of method on the clinical dataset. So the information shown here is the property of the data collected used for this study. Patients with indicated mitral and aortic valve disease were recruited to undergo multimodality imaging, and the data collected were anonymized. For each patient, 2D time series echocardiography scan and retrospective gated cardiac CT volumetric scan were acquired preoperatively on the same day. All data used in this experiment were collected retrospectively under a protocol approved by the Research Ethics Board of National Heart Institute Kuala Lumpur, Malaysia. The proper registration method consists of three major steps: temporal registration, noise reduction, and spatial registration. We will look each step at a time. First, is the temporal registration. Temporal registration was performed to synchronize echocardiography and cardiac CT image in time because both modalities produce images of different sampling latency and temporal resolution. Depending on heart rate and frame rate, echocardiography typically depicts a pumping heart moving through systolic and diastolic phases during surgical navigation. On the other hand, cardiac CT volume was captured at a single time point, typically at a dystolic phase. During preoperative assessment, since the shape of the heart varies over diastolic and systole, it is critical to correctly select the 2D planar echocardiography image to ensure the success of spatial registration with the CT volume. In this study, temporal registration of both imaging modality was achieved by time stamping using ECG gating signal that were obtained concurrently during echocardiography imaging. In the ECG signal, the R peak were automatically detected based on the amplitude of the signal in the signal. In order to select echocardiography images with similar cardiac phases to the preoperative cardiac CT volume, the ECG signal was linearly interpolated within the RR interval. In this study, three frames located within 40 to 70% of the interval were chosen for the spatial registration. This interval was determined from the capturing time delay recorded in the CT header file and was found to reside close to the end diastolic phase of the cardiac cycle. The second step is speckle noise reduction. Removing speckle noise hence is significant to improve the registration accuracy. Media filtering is often adopted to suppress noise, aiming to smooth the mutual information function from improved registration. However, this filtering undesirably blurs the boundaries of the anatomical structure. Instead of medium filtering, speckle reducing anisotropic diffusion (SRAD) is adopted to reduce the speckle noise in echocardiography images. This approach is based on both additive noise reduction anisotropic diffusion and multiplicative noise reduction. SRAD confer one main advantages over other conventional filtering methods, such as preserve and enhance edges while suppressing the speckle noise. So the third step is the spatial registration, which is the crucial part in this study. The echo is 2D planar image, while CT is 3D volume image. It is important to register 2D echo into 3D CT volume correctly. To perform spatial registration, 2D 2D to 3D intensity-based registration scheme was employed, utilizing mutual information as the similarity metric and pattern search algorithm as the underlying optimizer. In the registration process, the 2D and 2D planar echocardiography image was specially maneuvered within the vicinity of 3D volume to search the best matching cardiac CT plane. The seat position to search for best matching plane of CT was started off by assigning and placing the echographic image at the seat position. The seat position is dependent on the selected views for registration with cardiac CT. This seat position include the orientation and position of the heart valve, which were estimated and provided by the expert during pre-procedure planning on CT volume with respect to the 3D axis of the patient body. The special transformation T consists of 8 degree freedom was applied to the 2D echography images consisting 3D translation, 3D rotation, and 2D scaling. The linear interpolation was implemented to on the cardiac CT volume to sample 2D CT plane in the same size and the same location as the echographic images. The best matching interpolated 2D CT, and therefore the optimal alignment was determined using the normal mutual information. The the image registration time was performed iteratively using generalized pattern search GPS algorithm to find the optimal spatial transformation parameter that maximize the NMI measure of overlapping image pixel intensity. The optimal transformation found was subsequently applied to the cardiac CT volume to create matching 2D CT planar image. This image can be fused with echocardiographic image to create a composite image for the surgical navigation. So validation for the methodology suggested, we did it with comparing with manual registration. For this study, there are qualitative and quantitative validation be conducted. For qualitative validation, an overall interpolated cardiac CT was scored by the expert, and the inter-observer agreement for image quality cardiac structure for mobility VCT will expressed as a coherent case statistic. While for quantitative validation, expert will segment the echocardiography on and both CT, which is from the manual registration and automatic registration. For the segmented images, GSC and HD metric were calculated. We also measure the diameter of the aortic and mitral valve annulus and see the agreement in the diameter measurement and compare it using the Blunt-Altman plot, and also calculate the root mean square error to analyze the transformation parameters validation. So shown here is the result for one patient. The first row are the echo image of three different views which were crucial for the aortic and mitral valve disease, which is extracted out during the temporal registration, while the second row is the automatic registered CT resulted from the proposed method. Based on visual inspection, we can see the automatic registered CT image were found to match its corresponding echocardiography view. We compare the result with manual registration. The manual registration results are the gold standard, and based on visual inspection, there is no much difference between them. The experts will also score both images in terms of their overall quality. Based on the result of 90 images, about 43.4% were scored excellent, while the remaining is good. This means all structural information between manual and automated registration CT were identical. The DSC and HG were calculated on segmented structure. Based on the table, we can see that the DSC were above 0.7, which means both types of images have considerable similarity in the area size and spatial overlap. While HD, the magnitude were comparable in the magnitude to about 3 to 4 pixels in the resolution of CT and echocardiography. For Blunt-Altman plot, the difference of aortic and mitral valve diameter measured between CT plane from the automatic and manual registration method, we can see that 95% limit of agreement, which is the black dotted line, and the bias, which is the blue line. Both Blunt-Altman plot show no significant bias for both registration methods. To analyze the transformation parameter between automatic and manual registration, the RMSE were calculated. For translation were between 0 to 2.1 millimeter, which is comparable in the magnitude of 0 to 5 pixel of the resolution of cardiac CT and echocardiography. The angular deviation is less than 3 degree, and the minimal scaling deviation also too small. The fused image also shown both modalities were perfectly aligned together. The major finding for the study, the automatic registered CT were found to match its corresponding echocardiography view, which were extracted out from the time series data set at the temporal set registration step. Without optical tracking system mounted on the echocardiography transducer, the proposed method has shown the practicability to be utilized during the intra-procedural navigation during the replacement and implantation of the valve treatment. Promising accuracy of the proposed technique can be seen to be applied for the navigation during these procedures. So, to compare to other or the past related study, we can see that the distance error of the proposed registration framework is lowest as compared to other related studies. So the primary objective of this work is to fuse the 2D planar echocardiography images with cardiac CT volume. This is the first discussion of image registration with no optical tracking information provided to aid the process. So the registration produced an interpreted cross-sectional view from the cardiac CT volume, which matches the echocardiography image during the navigation process. The proposed technique could be applied in the image guidance and diagnostic procedure for the valve replacement and valve implantation procedure. The result indicate the promising accuracy of the proposed technique to be applied to intra-procedure navigation during the replacement and the implantation procedure. The contribution of this study is twofold. First, it introduced a multimodal registration framework to guide the intra-procedure navigation during the replacement and implantation for aortic and mitral valve disease, and also presented algorithm which perform with no optical tracking device, and therefore augmentation to echocardiography transducer probe is not necessary. As a suggestion for the viewers and also for the future researchers, there are a lot of opportunity for the future work. Such as my suggestion includes the intra-procedure guidance for the cardiac treatment using the echocardiography and cardiac CT fusion. Not only can be applied for the valve disease, but also for other cardiac diseases such as atrial defect treatment, atrial fibrillation, and irregular heartbeat disease. There are no comparative study of echo CT and echo MRI fusion in the literature. So there's another suggestion from me. Other than that, this technique I think can be applied for other anatomical structures such as for liver and also for the lung. For liver, such as for the hepatic intervention, and for lungs during the radiation therapy procedure. So these are some of my publication throughout my studies during my PhD work until right now. There are few on the image registration. I hope that as a viewers you can go and read and also have the opportunity to kind of like do like continuous studies from my research. There are some again, and this is some of my research interests, such as for the biomedical engineering, for the healthcare prototype development. So for this study, I would like to express my gratitude to PPPI grant from University Malaya, more for the Ministry of Science, Technology and Innovation Science Fund, and also to USIM for sponsoring my studies. I also like to thank to the IJN staff, especially to Dr. Ahmad Khairuddin, Sheikh Nur Faniza, and staff of National Heart Institute for the data collection, and for my supervisors, family, and friends. These are some references that I use for these studies. With that said, I conclude my presentation with thank you, and I hope that if you guys have any question, comment, I'm happy to receive it during the chat session. With that said, I would like to thank you again to the viewers and also for the KoSiST committee member. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and a very good day. So for today, I would like to present on our research with title Enhancing Microwave Absorbing Properties of Nickel Zinc Ferrite with Multi-Wall Carbon Nanotubes Loading at Higher Gigahertz Frequency. So my name is Pak Zida Muhammad Idris, and I am from College Genius Inison, USIM. So for today's presentation, outline is introduction, methodology, results and discussion, conclusion, and finally references. So for the introduction, microwave absorbing materials have continued to attract significant interest in recent decades in reducing spurious radar cross-section, especially in gigahertz frequency range. So this can be carried out by dissipating the magnetic or electrical fields of the wave in the form of heat, since electromagnetic waves have both components. So compounds of relatively heavy metals or ceramics are typically magnetic absorbers that play a role in regulating both complex permeability and complex permittivity. So both these complex permeability and complex permittivity are the most important parameters. Okay, so conductive fillers such as carbon black, multi-wall carbon nanotubes, carbon nanofiber, short carbon fiber, silver powder, and others have been used as dielectric absorbers. And carbon nanotubes have been found to have an overwhelming response in the study of producing CNT-based products. Meanwhile, nickel zinc ferrite cannot satisfy the demand of the ideal absorbing materials with the defects of narrow absorbing band and mass density. So what we try to do in this research is that we try to mix between magnetic material and dielectric material so that it can fulfill our parameters, that we can get suitable permeability and permittivity that can absorb the electromagnetic wave at higher frequency range or at gigahertz frequency range. So in order to have thin thickness, lower weight, wider absorption bandwidth, and good absorbing characteristic, we try to mix or substitute nickel zinc ferrite with the multi-wall carbon nanotube to produce new absorbing materials that can absorb the electromagnetic wave. So for methodology part, preparation of ferrite nanopowder, which is nickel zinc ferrite, by milling it by using high energy ball milling for 10 hours. Preparation of different amounts of MWCNT mixed with ferrite, which is from 2 weight percent of MWCNT until 6 weight percent. Preparation of filler incorporating into polymer matrix, pouring into sample holder, curing at room temperature, and finally send for sample characterization. So for sample characterization, we are doing it for morphological analysis, magnetic analysis, and microwave characterization. Results and discussion. Micrograph analysis. This is a TEM micrograph of multiple carbon nanotubes which was randomly entangled and cross-linked nanotubes with average size of 13.5 nanometer. And this is the nickel zinc ferrite. It was found to have an agglomeration of particles attributed to the milling process, and the distribution of particle size is in the range of 40 nanometer to 100 nanometer. However, after milling process, the average particle size obtained was 89 nanometer. Phase analysis by using X-ray diffractometer. So this is for pure multi-wall carbon nanotube, pure epoxy resin, and nickel zinc ferrite. So you see that for pure MWCNT, so 002 plane is the main peak. And there are also remaining multi-wall carbon nanotube peak, which is weak peak. And there is also the remaining peak demonstrated that the presence of catalyst, that is CO and MO. So this is presence of catalyst. So for pure epoxy resin, it is slightly harm here. So it is assigned to amorphous structure. And this is the nickel zinc ferrite plane. So it shows that proper formation of the ferrite crystallographic phases. Okay, so for the next phase analysis, which is we try to mix between MWCNT and nickel zinc ferrite with different weight percentage from 2 weight percent until 6 weight percent. So it can be found that all peaks were shifted to the right relative to the synthesized nickel zinc ferrite powders mixed with different weight percentage of MWCNTs. Additional peaks were absent in the sample although being mixed with MWCNTs. So this is due to the limitation of X-ray diffraction in detecting smaller concentration of MWCNTs being mixed in the composite sample. So increasing the amount of MWCNT shows that not much change in the intensity of the peak since the amount being mixed was too low. So we try to mix until 6% since beyond it will not produce an optimized result for our electromagnetic wave absorbing materials. Yeah. So this is the microstructure analysis. and we are taking it for the cross-section part. All the complete samples shown were after freeze fracture in liquid nitrogen and gold coated. So MWCNTs with their weak van der Waals forces between them will spontaneously attract each other in order to form MWCNT bundles. The arrow and rectangular shape were referred to the epoxy resin and MWCNT respectively. So nickel zinc ferrite particles and MWCNT immersed in the epoxy resin were referred to the circle and oval shape. So we try to produce it because we can get the three-dimensional network structures were generated through the interfacial interaction of MWCNTs, nickel zinc ferrite, and epoxy resin. For elemental analysis, this is the results of EDX pattern. So it reveals that there are C, which comes from the multi-wall carbonate tubes, whereas nickel, zinc, ferrum, and oxide were from nickel zinc ferrite, and the element aurum originates from the gold coating on the sample surface. So for MH hysteresis loop, the magnetization curves indicate presence of mixed state of ferromagnetism and superparamagnetism. Ferromagnetism comes from the sigmoid shape and the coercivity. So whereas superparamagnetism is due to the smaller grain size. So you can see from the table here, the coercivity value, saturation magnetization value, and retentivity. So as we increase the weight percentages from 2 weight percent until 6 weight percent, MS value is decreasing. Same goes to MR value, which is decreasing, and it is most likely due to the presence of higher multi-wall carbon nanotubes amount and structural distortion in the ferrite surface that reduces the magnetic moment. So the decrease of the saturation magnetization is due to the presence of non-magnetic multi-wall carbon nanotubes, and from this research we have found that the pure epoxy was 0.009 EMU per gram, and MS for pure nickel zinc ferrite is 68.2. So probably could only contain single domain in the sample, and the absorption of the magnetization was only due to the response by spin. So this is for the reflection loss speed. So for pure epoxy, resin matrix has almost no absorption at this frequency range. So this is for 68% of nickel zinc ferrite, 2% of MWCNT mixed with nickel zinc ferrite, 4% and 6%. So we can see that, for example, here this is 2 mm and this is 3 mm. So as we increase the thickness of the sample, the reflection loss is shift towards much lower frequency range. So for example, this is 2 mm and 3 mm. So increase it, we try to increase the thickness, the reflection loss is towards lower frequency range. For 1 mm, it is at much higher frequency range and it cannot be seen in the figure. So for all of this sample, the highest reflection loss was achieved when the multi-wall carbonated content was 2.8%, and the reflection loss of multi-wall carbonated nickel zinc ferrite with thickness of 2 mm was below -10 dB, which represent 90% of the electromagnetic wave being absorbed, with in the range of 14.5 GHz until 17 GHz. For conclusion, different weight percentages of multi-wall carbon nanotubes mixed with nickel zinc ferrite were synthesized and uniformly mixed and dispersed in the epoxy matrix. So the addition of only 2% of MWCNT helps in enhancing the microwave absorbing ability. The electromagnetic absorption of pure MWCNT was contributed to the dielectric loss, while for pure nickel zinc ferrite particles, the effect of magnetic loss, such as eddy current and other magnetic losses, become dominant over the dielectric loss. So the reflection loss peak moved towards lower frequency range as the amount of MWCNT was increased, showing that the working frequency can be tuned just by increasing MWCNTs according to the application needs for a certain frequency range. So our studies indicate that the samples may have potential applications as electromagnetic absorbing materials. So this is the acknowledgements, references, and that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all of you. Ladies and gentlemen, today I want to present about my research titled The Fabrication and Characterization of Low-Cost Raw Coconut Husk and Activated Carbon Coconut Husk Incorporated into Epoxy 3D Printed Honeycomb Structure as Electromagnetic Wave Absorbing Materials. My name is Raratul Insyirahmati Miswan, and I am from KoSiST Genius Insan. But why do I want to conduct this research in the first place? Well, that leads us to my problem statement. My problem statement is that I want to overcome the increasingly serious radiation pollution, which was increasing along with the development of technology. This technology radiates electromagnetic interference (EMI) that can be hazardous toward humans' health and the performance of devices. At the same time, I can decrease the amount of agricultural waste by using it as the filler in the fabricated device. And of course, last but not least, I want to synthesize and investigate the electromagnetic wave absorption properties by varying the materials content being incorporated into the epoxy 3D printed honeycomb structure at different thicknesses. The purpose of this research is to identify the most low-cost and suitable carbon material from agricultural waste to be incorporated in the structure of an electromagnetic wave absorbing material. Other than that, it is to absorb unwanted electromagnetic interference (EMI) radiated by electrical devices by introducing 3D printed honeycomb structure to maximize the absorption of EMI, reducing health hazard. The method I used for this research was constructed after reviewing journals. And the first one is to collect the agricultural waste, which for my research were the raw coconut husk and activated carbon coconut husk. After that, we have to dry the raw coconut husk in the oven at 60 degrees Celsius overnight. This is to evaporate any excess moisture from water so that it won't bring any malfunction to its crusher in the next process. The crushing process involves the filler material, which is the raw coconut husk, for it to be in powder form. Note that in this research, we use commercially obtained activated carbon coconut husk in powder form. Next, we mix the filler incorporated into matrix in a beaker by using a glass rod. After reviewing various sources, we decided to use epoxy and hardener as the matrix with ratio of 4:1, while for the ratio of filler and polymer matrix, we use 1:9. After that, we pour the mixture into the 3D printed honeycomb structure. Then, we cure it at room temperature overnight, and the finished sample was sent to University Putra Malaysia for sample characterization using vector network analyzer and field emission scanning electron microscope. So as you can see, this is the sample preparation in this research. We used 40mm activated carbon coconut husk and 40mm raw coconut husk. And the picture beside it is the after condition of the filler sample. The potential of coconut shell powder (CSP) and coconut shell activated carbon (CSAC) composites as electromagnetic interference (EMI) absorbing material is the title of the journal I mainly reference to. The journal shows the desirable potential of raw coconut husk and activated carbon coconut husk to be used as EMI absorbing material in terms of carbon as dominant element, mesoporous porosity, and thermal conductivity. The second one is the ultra-thin metal material microwave absorber using coconut core fiber over X-band frequency range. This journal shows the absorbing properties of coconut core fiber over X-band frequency range. It also proved that coconut core fiber substrate shows a better result compared to FR4 substrate. Lastly, ultrasonically synthesis dielectric microwave absorbing material from coconut core dust. This journal shows that the sample with 40% of coconut fiber dust has potential to be used as an alternative material for microwave absorber application compared to other bigger percentage. The samples fabricated were flexible and lightweight. They were also 1 mm and 2 mm thin. The sample is expected to enhance electromagnetic wave absorption properties as a result of the multiple reflections and porous structure which due to the outcomes of morphology and honeycomb 3D printed structures. The data collected from this research can be used as a reference and guidance for the development of new and improved electromagnetic absorbent materials in the near future. As you can see, the figure underneath the text is the picture of our research fabricated samples. As a conclusion, raw coconut husk and activated carbon coconut husk incorporated into epoxy 3D printed honeycomb structure has been successfully fabricated. This composite sample is expected to produce excellent electromagnetic wave absorbent performance and further to be used as an electromagnetic wave absorbent material in many applications. These are the references made for this research, and with that I thank you.
Assalamualaikum, hi and good morning. My name is Mazam Fahmi bin Mohtar and I am from College Jenis Insan USIM. So today, I'm going to present my research, which titled The Electromagnetic Wave Absorbing Performance of Low-Cost Agricultural Waste Epoxy 3D Printed Honeycomb Structure at Higher Gigahertz Frequency Range. So, the problem we face nowadays, smart devices such as smartphones, laptop and all that produce harmful electromagnetic pollution due to the electromagnetic interference, which is we can call it as EMI. This EMI would affect the human's health, which cause dizziness, headache and others. So, the solution is we propose to fabricate an electromagnetic wave absorbing materials that can absorb the unwanted signals by using agricultural waste, which is rice husk and burnt rice husk, to be used as filler incorporated into epoxy as polymer matrix. It was then further poured into 3D printed honeycomb structure. So, this is the diagram which shows how the absorption phenomenon occur. The white rectangle one represents the absorbers. When an incident rays hit the absorber, some will reflect it and some will absorb into the absorber. A good electromagnetic wave absorber is the one that has the lower energy dissipated from the reflected wave as more energy has been absorbed by the absorbing materials. These electromagnetic absorbers are able to decrease the EMI pollution while minimize the impact of agricultural waste on the natural environment. For the methodology, firstly we collect the rice husk and burnt rice husk by commercial. Then we powdered them by using crushing machine up to 12 minutes each in order to get fine powder size. Then the powder incorporated into polymer matrix. For the polymer matrix, we use epoxy resin and hardener at fixed ratio 4:1. For the composites, the filler ratio and the polymer are 1:9. Then the composite are poured into the honeycomb 3D structure and then cured overnight at room temperature. And the last one, it will characterized by using vector network analyzer and field emission electron microscope. For the literature review, this paper, which is titled Improved Rice Husk Ash Microwave Absorber with Carbon Nanotubes, presents the improvement of rice husk ash microwave absorber with adding carbon nanotube into the composites. The results show that the additional 2 weightage percentage of carbon nanotube adding into the rice husk ash composite increase the dielectric properties of rice husk ash carbon nanotube microwave absorber. Other than that, this paper is titled as Experimental the Microwave Absorption of Rice Husk and Rice Husk Ash Mixture presents about the different microwave absorption for different ratio of mixture of rice husk and rice husk ash. The results show that the best ratio for rashas and rashas admixture is 3 to 1 that absorb from 46 to 76 absorption. And the last one, this paper, which titled as Polymer Carbon-Based Composites as Electromagnetic Interference Shielding Materials, discuss about the efficiency of composites to absorb the AMI radiation. The use of honeycomb structure enhance the mechanical properties of the absorbers. So here are my literature review table, which I collect from the journals that I have read to be used as my reference. For the expected outcomes, high electromagnetic wave absorption was expected due to the effects of morphology, porous structure, and 3D printed honeycomb structure. This may help in having multiple reflection in the composite sample in order to obtain good electromagnetic wave absorbers. For the conclusion, Rashas epoxy 3D printed honeycomb structure has been successfully fabricated. It is also potential to be used in microwave absorbing application. So here are my references. That's all from me. Thank you.
Today I am introduce myself. My name is Andrew Islam. I'm a student in intellectual and today I'm going to present this conference. My advisor, Dr. Nader Yassin, and Dr. Mohammed Asman, my tutorial title, a critical review of CPS in green solar system. We are combinedly writing here and Dr. Nader Yassin and the Tuban Sawa and Dr. Kabul Arman and Nasir Amin. Review of but increasing energy demand, reliability, development of clean solar means various types of solar cells like light development of structure. We are focusing on CPS increasing because it is not specific to the environmental trend. The power of conductivity in CPS is increasing 30% indicate that it's developing. And for the energy, energy synthesis property, XRD, Raman, EDX, and XRF technology is used here. For synthesis of this thin film, like CTS and different physical methods, we used among all the sputtering methods, electron beam deposition, vacuum evaporation method have exposed better efficiency and high production quality and reliability. Additionally, breadth, the composition, variation of thickness, and structural defect and electrical composition, quality of absorber layer effect on this performance. In this paper, we have discussed the post-annealing treatment, CTS-based solar cell synthesis. It's important to improving the thin film properties of thin film. This paper describes the reason of efficiency, reducing also scope of the future research. The keyword of this article, the CTS, of this article. We know about the CTS, know about CTS structure, we know about CTS future research. Interaction. Energy demand, most promising solution to meet present user energy demand. For increasing efficiency and decreasing the cost solar cell is now is trading. It is semiconductor material that initiates electrical energy. Now, photovoltaic-based solar cells produce 1% of the world energy production. Now, solar cell based on crystal silicon research power, rich power conversion ability is different. So, thin is one of the remarkable position because it uses less raw material. Within thin film solar cell, percent to 2.6% for CBT, cadmium fluoride, and CIGS based solar cell, including low temperature coefficient. CIGS production depend on the ready material like Fe and helium. Due to lacking of raw material, it cannot um, use. Also, price can be increased suddenly. Cadmium fluoride. Cadmium is a toxic material based on tellurium. It's comparatively rarely element. So, researchers focus on environmental friendly solutions. For this, JDS is the example. Its material property on band gas is same CTS, though the power conversion efficiency is less than CDT and CIGS. CTS absorber layer is environmental friendly and based at low cost and its raw materials are available. CTS is P-type semiconductor that contain high coefficient of absorber coefficient and allows 10 to the power 4 centimeter per second. And also it's contain tunable bandwidth 1.1 to 1.5. That is the efficiency for photovoltaic absorber. The current highest efficiency of the CTS is 4 to 6%. Theoretical efficiency is about 30%, which is quite high. Physical and chemical, both method are synthesis applicable for the CTS-based solar cell, including physical method, sputtering, e-beam evaporation, co-evaporation, ball method, etc. For chemical method, we use here deposition, Sailor, spray pyrolysis, etc. most common. Physical methods are costly, more complex, but its future the product is used and so used physical method is more perfect. Though chemical method are cheaper and very few material waste, so the chemical method is also better. The production of another logic. So it is clear that both methods have benefit depend on the expected outcome. Post-annealing treatment has a vital role to increase the efficiency. And the efficiency as open circulation, circuit voltage and short circuit density and field factors And CTS thin film solar cell depend on the band gap, depending especially band gap, crystal structure, annealing temperature, along with the synthesis process. This study focused on the efficiency of CTS based analyzing different physical and chemical methods and various parameters. Though the chemical methods are cheaper and very few material waste, so the chemical method is also better for the production in another logics. So it is clear that both the method have benefit depend on the expected outcome. Post-handling treatment had vital role creating efficiency. So, this study focused on the CTS by the analyzing different physical and chemical methods, the various parameters. Basic structure of CTS. Now discussing the basic structure. If we follow this basic structure, the substrate, first is substrate. After the substrate, we can put up here the molybdenum layer. After that, it's a P-type CTS. Okay, P-type material we can set up here. Then we can N-type CDS material. After that, we can set up the window layer, zinc oxide. After that, another layer we can set up here, TCO layer. This is under window layer, and the contact level grid we can use the silver. This is the basic structure of CTS device. And CTS properties. CTS have the crystal structure, composition, and morphological properties, and optical properties, and electrical properties, and the basic structure of CTS. We'll discuss in this article. And here, this is a crystal, CTS crystal structure. So in here, here we can show the morphological structure and the cubic structure. And CTS the screen deposition technology. CTS screen deposition technology have two types. One is a vacuum deposition technology, and another is a non-vacuum deposition technology. So vacuum deposition technology is the evaporation, scattering, and fast laser deposition. This creates the visual. Okay, evaporation. Evaporation is one of the established vacuum thin film deposition method, and CTS thin film was fabricated first time with direct evaporation technique. And secondly, we use the sputtering. Sputtering is the most important methodology or technique. The sputtering method is one of the best suitable and the most controllable technology and comparative all vacuum-based technology that might be applied in a thin film production in commercial level. The first reported CTS thin film using the sputtering is the year 2010 by the Fernandez effort. In this study, the sample were sequentially deposition the element copper selenium target using DC magneton deposition during 10 minutes, whereas the power density is 0.1 W sitting to the second and 0.1 W watt per centimeter square respectively. The deposition was carried out the working pressure 6 into the power inverse 6 6 okay m bar and and the 2 into 10 to the power inverse 3 argon atmosphere um, with in base in argon atmosphere base. The sample were sulfurized at the temperature 350 degrees Celsius, 400 degrees Celsius, and 500 degrees Celsius during the sample deposition. The first CTS solar cell was fabricated using sputtering technology by the Umm In this study, sputtering argon atmosphere, including working power zero point 0.1 Pascal, as well as using copper and strontium DC gun at RT. And the sulfurized two different way condition like as the normal atmosphere and the and there is another is the presence of gallium sulfide. Whereas the effect of germanium is allowing in the performance of CTS alloying. They got the band gap 1.2 electrovolt for the CTS alloy uh, with germanium. The cubic phase that shows the great efficiency 6.1%, and in the ratio 0.017 to 0.83 by 0.83, and germanium by strontium ratio. And in contrast, non-alloyed solar cell shows only 2.13%. Non-vacuum deposition technology. The various issues have been suffering in the non-vacuum deposition. That is the barrier of getting higher efficient solar cell. Hence, vacuum methods are costly than the non-vacuum method synthesis process, which is commonly important. CTS film deposition technique. Non-vacuum deposition technique, ball milling, and solid state reaction, and electrodeposition, chemical bath deposition. Those are the non-vacuum deposition techniques. Now we're discussing the ball milling technique. Nominated 2014 synthesis CTS thin film by ball milling, followed by the post annealing treatment, the high pressure sinterized air, 6 megapixel, followed by the subsequent sulfurization. The copper by strontium ratio 1.9, and the post annealing treatment is 600 degrees Celsius, showed 1.3 efficiency. Navsatel 2016 succeed in improving the morphology by using spark plasma sintering process. Centering process. And the sintering was done at 600 degrees Celsius for the 5 minutes at 50 as MPa, which ensuring the formation of pure CTS. The morphology was found by complex, uniform, and highly crystalline, which is favorable for the solar cell application. Nomoratel. Okay. Solid state reaction. Solid state reaction. In solid state reaction method, the precursors are mixed, reduce the particle size by the ball milling to develop extreme surface area for accelerating the rate of reaction. Actually, it is a long established procedure of fabrication to getting desired compound. Reaction. In solid reaction, reaction method, predecessor are mixing, reduce the particle size and ball milling to develop mixer surface area and accelerating the rate of reaction. Actually, it is the long establishment process fabrication to getting desired compound. Electrode deposition. The sulfurization of electron deposition process was described for the fabrication of CTS thin film solar cell by the Bragg et al. The highest efficiency of CTS solar cell was achieved in the electrodeposition method by the Kokari et al. This study analyzed the effect of deposition ratio covered by stadium on the field properties, varied deposition time to obtain the different ratio of copper by stadium as well as the photovoltaic device performance. Therefore, the CTS device fabricated structure SLG substrate, after that molybdenum, after that CDS, after that zinc oxide, and aluminum alloy. And heating efficiency was 2.84%. The ratio copper by sodium was 2, it's 2 less than 2 or equal to. That is the highest efficiency regarding the electrodeposition method. Chemical pathway. The first CTS chemical solution was fabricated using chemical pathway by the Neo et al. This sequential deposition of the copper sulfate and copper titanium sulfide layer using CVD and following by the annealing nitrogen environment for the fabrication of CTS chemically. And the copper sulfide layer converted into copper, the copper 8 and sulfur 5 at the annealing temperature 302 to 340 degrees Celsius. That was the react with the stinium, sulfur and temperature of 400 degrees Celsius. The estimated direct optical band gap was approximately 1 electrovolt, whereas in the dark condition, the electrical conductivity was measured as the 1 ohm, the one ohm inverse 1 and centimeter inverse 1. The chemical deposition process was studied for the CTS chemical fabrication by the Evelyn et al. 2010. The chemical deposition process was studied CTS thin film fabrication by the Evelyn et al. 2010. Hence, the sequential deposition of 200 nanometer thick layer and the copper sulfate and 180 nanometer thick layer of strontium sulfide were used CVD method. There were indeed 350 degrees Celsius and 400 degrees Celsius and nitrogen environment for the field deposition process. That's conclusion. In conclude, the history of CPS solar cell was reviewed. This article reviewed the history of CPS solar cell was reviewed, and also discussed past successful CPS device and present update research work regarding the field. Therefore, to understand the material properties of they discussed the characteristics of CPS thinking device. Although the detail were discussed here, like the compositional and crystal structure, optical morphological, and the electrical properties and the fundamental property structure, CPS solar cell was discussed. And different methodologies also described briefly for the fabrication. This paper also suggested the scope of the future research using like grouping recipients in different materials. Thank you guys for listening my presentation regarding CTS regarding how this article is a critical review of CTS in the solar space. Thank you guys. There uh, can include here some reference to you all.